A discrete graph is composed of distinct points. So I'm trying to think of, like, if I was charting how many hamburgers kids ate at lunch today. You can't go to the lunchroom and only have a half a hamburger. You can't have 2.5 hamburgers. You can't have 1 1/3 hamburgers. They're going to give you a burger. So it's an exact amount. Okay, there's nothing in between. But you would have like a continuous graph if you were plotting something that's more fluid. So something like time, or like I think about if I was measuring how many gallons it took to fill up a swimming pool. Those are things that you have like little numbers in between. And so it's not like an exact, like, oh, we put 52 gallons in here. We might have put 52.2 gallons in. Or maybe they would be graphing how long it took kids to go through the lunch line. And so something like that was more fluid, okay? Because it can be, hours can be broken down into minutes, and minutes can be broken down into seconds, and that kind of thing. So a discrete graph is very exact points, things that usually can't be more fluid, and a continuous graph is composed of like lines or curves. So this will make more sense as we continue. It says relating graphs to situations. So that's what we're going to start first, is where you need to read a situation and then you need to be able to match a graph to it. So it says each day several leaves fall from a tree. So several leaves fall. One day, so just quickly, a gust of wind blows off many leaves, and eventually there are no more leaves in the tree. So you can look at these three graphs and pay attention to the axis labels. So we've got time and we have leaves. That's why they are, it is a line, okay? So the first thing is I notice that in the first graph, the number of leaves goes up. In our situation, did we ever talk about the more leaves growing or more leaves showing up on the trees? No, the entire time we were losing leaves. So graph A is kind of out of there automatically. Okay, so then the next thing that I look at is that graph B or graph C has a flat spot. In our description, was there ever a time where the tree just didn't lose any leaves? No, okay, so the leaves did not stay consistent the entire time that I was talking. It was losing leaves. So then you're kind of left with a third choice, and you want to know, does this match up? So first, a few leaves fell off, and then do you notice how the line got steeper? It got steeper because of that gust of wind. And then eventually it did go down to 0 where there were no leaves left on the tree. So that is how I confirm that B is the correct choice. Okay, so this one kind of says on your own. I'll read it to you and I'll let you guys think about it for a second. The air temperature increased steadily for several hours and then it remained constant. So we've got increased steadily, remained constant. At the end of the day, the temperature increased slightly before dropping sharply. So pay attention to those key verbs. Choose the graph that best represents the situation. So why don't you guys just take a second and see if you can figure out what graph. We have time and temperatures are two different choices. Does anyone want to volunteer which one they think? Leah?
I think it's C.
Okay, you think it's C. Should we see if it works? So it increased steadily. So this graph is actually the only one that increased steadily, wasn't it? Yep. Okay, so then it remained constant. So here's the constant right here, the flat spot. Then at the end of the day, the temperature increased slightly and then dropped drastically, okay? Dropped sharply. Choose the graph that best represents, and there we go. Good job. Okay, the next type, it says we are going to practice sketching our graph. So sketching means that it doesn't have to be exact. You're just giving like a general example of what the graph would look like. And then you need to determine whether this is going to be a continuous or discrete graph. So Simon is selling candles to raise money for the school dance. For each candle he sells, the school will get $2.50. He has 10 candles he can sell. So the first thing that I think about are the fact that this is just going to be positive numbers. So I'm just showing the first quadrant. What are my two factors? What are the two things, Austin? Money and candles, okay? So later on in this chapter, we'll talk more about independent and dependent, but basically the money depends on the number of candles sold. So I do something like this, okay? And it's consistent. Every candle, he gets 250. So I'm just gonna mark, and I'm gonna only go up to 10 because he only has 10 candles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then on the other end, every candle is exactly 250. There's no differences. If he sells 4 candles, you don't get a deal. And so, oh, hold on one second. So we have candles sold and then the price. Now, because we're just sketching a graph, I am going to make each line go up by 250. So this would be $5. This would be $10. This would be 15. And notice how I try to keep all of my increments really nice and neat, but I don't label everything because we know what the line in between means. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Funny. Okay, so now I'm going to plot my points. So for 1 candle, he would get 250. For 2 candles, he would make a total of $5. 3 candles be $7.50. 4 candles bring us up to 10. And you guys can see how I'm doing this, right? It gets harder the further out you get from your. You usually have a ruler up here. Okay, so it's 7. So you guys could just take a moment to graph this. And your sketch doesn't have to be perfect. Just try to make it as nice and neat as possible. Okay, so you can see that this would be basically a straight, if I had a graph perfectly, it would look like a straight line. Because it's consistent. Every time we sell another candle, we get the exact same amount. Now, question for you. You have to determine, is this a discrete graph or a continuous? What do you guys think? So why do you think it's continuous? I'm just curious.
He's going to keep on selling candles and then it will keep on going up.
Okay, that is very true. Any other thoughts?
It can't be because he only has 10 candles, so he has to stop.
Okay, so you think it's not continuous because he has to stop, okay? And so this is why this is the trickiest part. It is not continuous, but not necessarily because he has to stop, but it's not continuous because I can't draw just a straight line through this. And the reason I can't draw a straight line through this is because this is technically not a dot. I can't sell half a candle for $1.25. I can't sell 3.5 candles. Macy, put that away. Let's see, I'm going to take it away. So because I can't sell partials, there are not technically points in between all of these dots, so I cannot make this a full line. So this is a discrete graph. And maybe I'll just put in parentheses here because each point is distinct. So that's the hardest part here. Uh-oh. Got some people entering late. Okay, so if you flip this over, we have another graph that we are going to sketch. This talks about Angelique's heart rate being monitored while she exercises on a treadmill. While walking, her heart rate remains the same. As she increases her pace, her heart rate rises at a steady rate When she begins to run, her heart rate increases more rapidly, then remains high while she runs. As she decreases her pace, her heart rate slows down and returns to a normal rate. So a couple of things. I like to kind of highlight each thing that changes. So while walking, so she's walking, her heart rate remains the same. She doesn't increase. As she increases her pace, her heart rate rises at a steady rate. Then she begins to run, her heart rate increases more rapidly. And then the other thing is that it remains high while she runs. Then as she decreases her pace, her heart rate slows down and returns to her normal rate. Okay, so if we are going to sketch a graph for this, and I keep reminding you that we're just sketching, we have probably down here would kind of be like the activity. And this is time. So we're not going to really say like runs, walks. And then I'm just going to say over time. So this would be like 0 minutes. And then this would be, however long it took her to finish her workout, 60 minutes. As long as you have it labeled, that's all that matters. And then this is going to be her heart rate. So if you just imagine even a graph that measures your heart rate, it's going to like go up and down like this. Okay, so do you think we start at 0? No, because she was alive when she started, right? So that means her heart rate is just going to start off somewhere here. And then it says that she was walking and her heart rate didn't change. Her heart rate didn't go up while she was walking. So for a little bit of time, she just was walking. And then as she increases her pace, her heart rate rises steadily. So it's going to start going up just a little bit, nice straight line. And then as she begins to run, her heart rate increases more rapidly. So that means our line has to get steeper. And then remains high while she runs. So then she ran. As she decreases her pace, her heart rate slows down and returns to normal. So I'm just bringing it back to where I started. So you guys can see how started off walking and then increased steadily. Then she started running, then it stayed high while she ran, and then when she slowed down, it came back to normal. Okay. So my sketches, notice I didn't have any numbers on this graph. And that's okay, because we're just sketching an image. Now, notice how my lines are connected. Is this a continuous or discrete graph? It's a continuous graph. Okay, so it's continuous because I didn't record exactly how fast her heart rate was going at every second. I just assume that between this measurement and this measurement, that's what her heart rate was somewhere in between. Okay, so now you're going to draw your own. Henry begins to drain the water tank by opening the valve. He then opens another valve. Then he closes the first valve. He leaves the second valve open until the tank is empty. Why don't you guys take a second? When we start, the water level is somewhere up here, obviously. Then it started to drain out. When we opened the other valve, it came out really fast for a little bit of time, but then he closes it, so it goes kind of back to that same rate. So your graph should look something like this. Okay, just something like it. It doesn't have to be perfect, but notice that it was 1 speed, then it got really fast, and then it went back down to 0. Okay. Okay, so the other little things that I want you to be aware of, like I've already been saying, is be aware of your axis labels. Both graphs show a relationship about a child going down the slide, but graph A represents time and the distance from the ground. So this one starts really high up because he's further away from the ground. And then at the end of his sliding experience, he's at the ground. The other graph represents the speed. So he starts off slow and then he increases and he gets to a max and then it slows back down. Does anyone know why it would slow him back down when he's going down the slide? What do you think? Pardon? Yeah, he got to the ground. And also if the slide like increased and then just dropped him, he'd probably like launch off the slide. Like I just imagine this little kid just boom, until he hit the ground. It'd be much more abrupt, right? So pay attention, these graphs look completely different, but they're graphing technically the same experience, just showing different variables, okay? So one was showing ground, distance from ground, one was showing speed. So pay attention to those types of things. And the last one is being able to write a situation for a graph. So this is like being creative, making it up, having fun with this. So this one has time and speed. And it could be absolutely anything that would be relatable. So something that can move. Okay, so you could have maybe that you could say Ralph leaves the expressway. You could say exits, whatever you want to say. He slows down as he comes to a county highway. He travels on the highway for a while, enters a town, and slows down until he stops at his mom's house. Okay, I totally made it up, but it makes sense. He was on the expressway, so he was going pretty fast. He slows down, he drives on the highway for a while. When you enter a town, usually you slow down until you come to a stop at his mom's house.